Thank you very much. Thank you, everybody, to listen to this talk. So it's not about a given talk. It's more about the development we have been doing in the Swiss Plasma Center over the last 40 years or so. So that we can have some perspectives of how we go from usual collaborations back in the 70s, 80s up to 2025 as we are now. And then hopefully we'll have some discussions also on methodology or other aspects. So I will take a few examples where I was involved slightly or mainly so that it related to my subjective perspectives, and that way I can justify being the sole author of that talk. So in the 70s, 80s, it started the large codes in finite element, a lot about MHD stability for photochromatic plasmas, starting also with new shapes and so on. So mainly it was a competition between labs, I would say, a good competition, but a competition between labs. Then we had more formal collaborations in the early 90s, moving to more automatic or standardized agreements, which allowed to have trust in the way that people would share the codes and would keep on doing so years after years. But now also with the upcoming of private industries, we have to formalize all this, and then we have to decide if we go open source or not. In the Swiss Plasma Center, we did decide some years ago to move towards open source as much as we can. And we have a list of codes you can see at the GitHub. I will show at the end. And I will start this journey from the know-how we get from the Erato code back in the 80s up to the most recent ones, and just ask a few questions. So the Erato code is an example of ideal MHD stability code, which was developed back in the end of the 70s, actually. And at that time, the way the codes could be shared was through the publication in specific journals like Computer Physics Communication, where you would give the source codes to the journal at the same time as you publish the paper, which becomes the documentation of the code. The good thing was that you had for sure documentation with the source codes. The bad part, of course, it was a given source at the given time, and you did not get the evolution and the modifications by other users. Now, nevertheless, this code was used for the Trojan limit, which showing that beta was essentially proportional to the normalized plasma current, hopefully up to very large plasma current and beta. And this was used actually for designing the TCV tokamak that we have in Lausanne, EPFL. We have the tokamak at configuration variable. So on the left, you have the paper when we did the prediction back in 1986 and published in 88, where we could do equilibria and stability of different shapes and different plasma profiles that we hopefully, which hopefully were reproducible, representative, of what we would get in the tokamak. And 10 years later, we have the tokamak and we could do the experiments and publish the results, which matched quite well the prediction actually, showing that after the elongation of 2.2, 2.5, then this linear dependence between beta and normalized beta, normalized current did not continue anymore. How we did collaboration? Well, at that time, it was through fax. We had documents, people would sign an agreement and send it back. I could find a few examples I will show you. So you see, this is in 1992. And of course, the paper is not so good anymore. This was not sustainable papers, but mainly what was being done is to say that people should not change the name of the code because in the past that had happened. Modifications are given back to the main owner with implicit condition that the main owner would share to everybody the modifications that he or she receives. and of course to cite the appropriate original work. And with this basic agreements, I found the oldest I found was in 1989 with this wave particle interaction code in a wave propagation code. On the right, it's the code from my thesis, so that's why I show it as well, but in 1992, 1994. So you see that this comes back from quite a while that we had these kind of agreements. It was formalized, but we did not have standard revision coding. So we then used SVN, and now of course we use Git. But so we started to have Git tags appearing even inside the document, but still with the same spirit. And this built up the confidence between different groups, and we could really collaborate in between groups quite efficiently on that aspects. The main ones at that time, in the end of the 90s, were Fortran finite element codes. For the tokamak equilibrium, the cheese code. For the ideal stability, now afterwards we use the cakes and kinks. And ICRF calculations, for example, Lion, which was mentioned also in the talk by Olivier Hernan. And these codes were used in different tokamaks and for example, in JET. But now, as I said, if we want to be more strict and correct with respect to copyrights and licenses, we need to have this contributor license agreement to be signed instead of just saying, we give back the modifications. We really allow then the main owner of the copyrights to choose if they want to go to open source or not. And that's what we need to be able to do that. So that's what we have been gathering for the last few years. And in the meantime, we had also changed the agreement to add a fifth part. This is point 4 here, that users which are within a cluster of codes installed within a cluster, they can use the code as installed. And this was to be able to put the codes at ITER, and so all the ITER partners, for example, could be using these codes. And related to the question that Olivier Hernan mentioned earlier, from the beginning of when we started the integrated modeling and Eurofusion initiatives, the SPC, we promoted codes within the ITER IMAS infrastructure, only those that we agreed from the start would become open source or would be really fully released within ITER. So all the codes which are inside IMAS from the SPC will become open source, as you will see in the list later on. Now, inside, as mentioned also earlier, inside Eurofusion, we had more integrated modeling initiatives to build frameworks so that we could have standards and more cooperative developments. Also with the data structure we could exchange between physics modules. That's where this interface data structures came out from these efforts, actually. We developed also the tokamak coordinate conventions in this respect. More recently, for the SPC, we focused on flight simulator, which could be used in real time. And at the same time, if we have fast simulation code, of course, we can do trajectory optimization, fast offline, in between shot simulations. And so this helps not only for real time, but also for preparing and developing attractive trajectories for the tokamaks. And this is being used, for example, with the MEQ suite, the forward Graf-Shafranov evolutive code, which Francesco Carpanese developed, was mentioned earlier by Nico, but we have also the inverse FBT or the real-time Yuki equilibrium construction. That's part of the MEQ suite, which is open source, and the Raptor fast radial transport predictive solver, which will be open source soon. We have to finalize the paperwork. We developed other small or tools or physics modules that are integrated in these activities. But of course, we continue to have big codes being developed, like Geokinetic or other codes at SPC. These are often mainly PhD driven. So we have a PhD and a thesis, which is around these codes. And the question is it compatible with open source? I would say it sounds fully compatible in some sense, because academic studies are supposed to be open and public, since it's using public money in some sense. However, often it was strictly for non-commercial studies, so that's where it started to be difficult sometimes to interact. And also for PhD thesis, they need to be original work, and in some sense, it's not a truly collaborative project, because we need to test the student that he's doing, really leading the project from the start. And since the start is often a bit slower, that's why we often protect a little bit, at least at the start of the project, the PhD student, so that he or she can develop the research properly. So sometimes it's not so compatible as one might expect. Often what we decided in the past is that we keep codes non-open up to the first publication of the PhD student related to the code, and then we can go open source, or more open in any case, but open source. Of course, the danger is that you never get the documentation, because maybe the student finishes just before the end of the thesis, or you need to make the open source after the thesis, so that means the supervisor has to do it. And or you continue with a new PhD student on the same topic, and then you want to protect again the new one, and then you decide not to go open source. So all these things you should prepare and think about a bit early in the process, so that these go smoothly through. Another question is how to sustain the codes which are developed in a PhD. This is often a big question in academia, and there the open source is really an asset, in the sense that it builds the community supports from the start, and hopefully we can keep on going using these codes and not of these codes coming from PhD thesis. The Lion is from Laurent Villard, the cheese code from Lutyens, the SEMAL from mine, although it's not used so much anymore, LOP5 from Alberto Bottino, and Raptor from Federico Bellicci, and I did not list all of them. Now, open source and private partnerships. Maybe it sounds fully incompatible, in the sense that open source products cost rather than make money. So what do? Private industry wants to protect the main assets. And what I would say to this is that the main asset is often manpower and know-how, and not really code. The code can be reproduced in some sense, for example, the thorax based on the Raptor code, and that's fine. What is important is in the manpower and the know-how, and this remains, and that's where education also comes into the game. And we want to help accelerating fusion, including with the private partners. It's nonsense to think that we would do fusion without the private industry. And so I think we should all together promote open source with the private sector. So that's the SPC point of view. And of course, being realistic, with some partners it works, with some others it does not so much. But I think now we start to reach a critical mass. We can concentrate on collaborating with those who like to collaborate. So what we do now, we of course we have GitLab. So what we develop rather in gitlab.epfl.ch, we have a local GitLab implementation, and this helps a lot on the CI/CD developments. We can also deploy automatically tests using the hardware that will be used, for example, in the TCV tokamak. So there are many ways that it helps, but we have a system to work with external collaborators, and so this is fine to work all together. and we are ready for the big collaboration. So now I just a few slides from the GitHub Swiss Plasma Center that you can see there. I prepared the README file before this talk. You see this SCDDS is a Simulink-based control design, which is at the heart of the PCSSP simulation platform shown this morning. And then you have the cheese code, the MAQ suite, and then you have a bunch of codes which will become open source soon, from 3D ideal stability, cubic spline, disruption event framework, polarization calculation, the Raptor I mentioned, the Lion code. So a lot of opportunities to contribute to these projects. And so as the final words, so the Swiss Plasma Center is dedicated to the open science and open source code developments. There's a risk, but there's also opportunities. So somebody needs to start taking the risk, and we decide to start. Given SPC missions, we do pay special attention to PhD projects, but we want to move earlier on in these with open source developments for the PhD thesis. And I think academia should be leading in bringing private partners towards open source development. Thank you very much.